Okay, so here's a brief overview of the Jetsonbot software optical avoidance version. So what we're looking at here is here's a picture of the Raspberry Pi cameras, the left and right. They're the NoIR version with the blue filter on them, and the front one is a Logitech USB web camera. So you're going to see the left IR here, the center USB, and the right IR are up there. So what this software does is it just takes the images and determines what are the obstacles in the background, and based on those it forms a horizon line, which you're going to see in green here. So basically, as the robot moves, it's going to process each of these images and keep track of how close the obstacles in the horizon get to the robot itself. So here you'll see the front camera has a warning, which is why the line turns red, and same with the right camera. And this basically means the left is shown clear, so it wants to turn left a little bit more than, let's just say, if the right camera had a warning but the front one didn't. So you can also see too that the images do not pick up very clearly. They're blurred, they're out of focus. Each of these images come in as a thread. So I think of each camera as a thread. There's 3 image threads, and then the main thread runs in the Jetsonbot that processes them all. So it turns to the left a little bit, but it's still saying that it's too close, and it also picked up that it's too close on the left frame itself. So in this case, it's probably going to back up, and it shows that the left is kind of clear just by a little bit. Turns left again. This also frees up the front camera, and the right one still shows a warning, so it'll keep turning right until it's clear. So here's where I've put a notebook in the frame as it's moving. So I'm standing off to the side here, just to show you that you can put an object in the path as the robot moves, and it'll detect it and try to avoid it. At this point the robot's very close to the obstacle, I should say. Sorry. There's my feet, so you can see it picks up some shadows. It turns away until it gets clear, and it navigates around. So you can see that it does pick up a lot of shadows. It's not perfect. Here's a good example right here. This whole area is really, the horizon should be up here, but it picks up the shadow, so the algorithm does need some tweaking to make it perfect. Now, object detection is going to be the next video, but to show you that the object detection is going to work below the horizon. So, for example, when the horizon's not perfect and it's actually giving you some of the obstacles as part of the underneath the horizon image, if this frame was processed with object detection, this would be an issue because it would probably want to lock onto things over here, even though that's an obstacle. So again, it needs some tweaking. It's not perfect. But the way these cameras are adjusted, and one reason why it's blurry is because these are flexible mounts, as you can see on the Raspberry Pi cameras. The normal RGB webcam is hard mounted, but it's also lower on the chassis, as you can tell from the images. These are kind of tilted down, so it kind of looks from above and down a little bit. And these can be quickly moved in different positions, which is the reason why it's on a flexible thing for experimentation. I've got parts on order to hard mount these to hopefully reduce some of that bouncing a little bit. But because the chassis itself and the way the cameras are aligned and the warning level that's written in the software, it's all calibrated so that even when the robot gets close to an object or an obstacle like this, it's not going to hit it. So you can see how close it is. It's the robot itself, if you're looking at it from third point of view, is it's very close to the obstacle, but it's not hitting it. And that's because frames will get dropped as it's moving forward, and the speed of it versus the speed of acquiring images and processing them will create some of these errors where it's got to turn a little bit too close. Like here's a good example when it picks up shadow here, it's going to think it's going to turn left, even though it had some room to go forward. But it's like almost like a dead reckoning. Like it just tries its best it can, and it doesn't hit anything. But like I said, it'll turn kind of quicker than it needs to sometimes. So if you're looking at it from the third person point of view, sometimes it'll make turns and stuff, and you're like, well, hey, you had space, you had room. But it's better to be too cautious than it is to run into things for safety. So here's a good example of where it dropped a bunch of frames as it was moving forward before it processed, and it got really, really close to this object. All three of them go off as warning, so the robot's gonna took another frame for it to actually stop, the Arduino command to actually stop, and then the process pick up. And what it does in this situation is it goes backwards. So you can see it's backing up a little bit, but it doesn't turn at all. So when it backs up, it still thinks that there's room to go forward. And again, it's just going to have to take this as an error. It's going to have to go through the process a couple times, and after a while it turns enough to make sure it's in the clear and keeps going. But this is basic obstacle avoidance. There's no route planning. There's no understanding of how much it can turn based on these warnings. It's just a combination of, well, does left or right see it, or front? All right, what if front and right sees it? What if left and front sees it? What if all three see it? It's a very basic configuration. So here's a good example. The base of this light you can see here, and then this big obstacle. So it's going to turn left, and now it's clear on the left and the front, but you can still see the base of the light is here, detected on the right. So it's got to turn left again. There's my foot, and it detects it again as I move it in front of the frame. Turns itself, and that's basically it for the obstacle avoidance basic roving around. The next video will talk about the object detection, which is extremely more experimental than this. Works only about 40% of the time, but hope you enjoyed that. And really, the OpenCV is pretty simple. Instead of going into details that could take hours, it's really a filter of the difference between the intensity of the images. So you want to kind of like dynamically threshold your image from what I call the bottom up to the top down, from like really intense down, and then from low intensity up, and then average them in the middle, and then start looking at what kind of contours are available and their sizes and location, how they relate to each other, in order to come up with this little obstacle avoidance. So thanks for watching.